Hey there, welcome back to CMTEQ channel. In power system, there is a concept of long transmission line, short transmission line, or medium transmission line. In this tutorial, we're going to analyze a short transmission line and also draw its phasor diagram. So if you want to get comfortable with this type of analysis, stay tuned until the end of this tutorial. Now, what do we call this short transmission line? Now, this is specifically important for voltage regulation. So if you want to run a voltage regulation at the side of the circuit, which is the receiving end of the circuit, well, you have to take account of the capacitive current because that will create some voltage drop. But in a short transmission line, something around 10 to 15 kilometers, the capacitive current can be considered negligible for line regulation calculation. But if you are dealing with long to medium transmission line, you have to consider capacitive current. But remember, this only applies to overhead transmission line. Okay, so if you are dealing with underground systems, remember the long, short, medium, they do not apply there, because there the cables are going to be too close to each other that you have to consider the capacitance that's going to build up around the bundles cable. As can be seen here on the normal overhead transmission line, the line spacing between the cable here can go up to 1 meters of spacing. But this is not the case in the underground. The cables are going to be bundled together, very tightly close together, and in that situation the capacitance are going to be much higher. So you cannot do an analysis the same way we do for overhead transmission line. Now, before we can draw the phasor diagram of these short transmission line equivalent circuit, we need to define the parameters for these diagram here. So the first parameter is the sending end voltage, known as V send, which has an angle of theta send, and this voltage will basically induce a current into this transmission line, and that is I send. Now we've got line parameters, so we've got the resistance and we've got the reactance, basically the inductance XL that will induce a reactance here, and this combo here, R and XL, will basically induce the impedance of the line, so that will be ZL, and ZL will have an angle theta that can be calculated. Now moving on, we've got a receiving end voltage. Now the receiving end voltage will be sitting right here at this point. Okay, so this is where the receiving end will be sitting just before the circuit breaker is closed. So once we close the circuit breaker, then we're going to attach the load on the receiving end of the circuit. By the way, if you want to know more about overhead line parameters calculation, like resistance of an overhead line, capacitance and inductance for overhead line transmission line, please watch the tutorial series on overhead line parameters calculations. I've got tutorial 1, 2, 3 that speaks about these parameters. You're going to learn a great deal of insight of this topic. The tutorial links are on the description box. Please make sure you watch those. But now this load here have an angle, and this angle will carry a sign depending on the type of load. Now first off, if it's a resistive load, which we're going to draw a phasor diagram just now, this angle is basically going to be 0 degree. And if it's a purely inductive load, then you're going to have a load impedance of plus 90 degree and negative 90 degree for a purely capacitive load. But also, as soon as the circuit breaker is closed, there will be a current that will flow here. Now this current is the load current, which basically is IL. Okay, and IL will have an angle as well, which will be plus minus theta L. Now the sign for this angle will also be dependent on the type of load you're going to be having here. If this load here is purely capacitive, that means the current will lead the voltage by 90 degree. In that case, you're going to have a positive angle here for the current. And inversely, if the load is purely inductive, meaning the current lags the voltage by 90 degrees, so you're going to have a negative angle of the current. So that is what you need to keep in mind while analyzing this type of circuit. And also do keep in mind that in a short transmission or in a transmission line, as we analyzing here, the sending end current will be equal to the receiving end current. Now we are assuming that we don't have a transformer in between our transmission line here. We basically just have a transmission line. Okay, in that case, the current from the sending end, I send, must then be equal to the current from the receiving end, because you are just dealing with a series circuit here. So you're going to have I send must be equal to I receive. Okay, but bear in mind that this only applies to the magnitude of the current. So in case you get a problem that they try to trick you, they give you an angle for this current here, you cannot equate that to this angle. Okay, so this angle here depend on the type of loads that you have here at the receiving end, whether it's purely resistive, capacitive, or inductive, or a mix of all that. Then it's going to define this angle here, and that cannot be equated to the angle from the sending end if there is any. Okay, so now having said that, since we've now defined all the parameters that we need for this short transmission line, we can then go ahead and draw the phasor diagram for the equivalent circuit here with a resistive load. So let's emphasize that the phasor diagram we're going to draw will be for a resistive load. So we assume that the load here is purely resistive. Okay, so this is for a resistive load. Now before we can actually proceed with the phasor diagram, there are two important elements of the phasor diagram that we missed. They are the voltage drop across the transmission line. So we've got R and we've got XL. So we know that the voltage drop here will be VR, and also on XL here we're also going to have a voltage drop as VL that will have a 90-degree angle, and VR will have a 0-degree angle, and together these combo here are basically going to be VZ. Okay, so that basically the total voltage drop across a transmission line, that will be VR plus VL, and this will have an angle that we can calculate, okay, while you are working this type of problem. So now we are actually ready, because now we've got all the parameters we need to draw the phasor diagram. To draw your phasor diagram, you first need to draw the reference voltage, which is V at the receiving end with an angle of 0 degree right before the circuit breaker is closed. Okay, so from the origin you're going to draw your V rec. So this is going to be V rec, basically the voltage at the receiving end. Then since the current is basically going to be in phase with the voltage, because this is a resistive load, then you're going to draw your current basically in phase with V rec. So this here will be your IL phasor. Great. Now the next thing to do here is the voltage drops. You now need to deal with the voltage drop. So the first one is VR. Now this voltage drop is caused by the sending end current that crosses this resistance, okay, which is equal to the receiving end current. So which means since R is purely resistive, so VR is also going to be in phase with your receiving end voltage. Okay, so that will be your VR. So this here is going to be VR. Now you need to draw the voltage drop through the inductor, okay, on the transmission line. Now this voltage drop is going to be perpendicular to your VR or to the VREC, because it is 90 degree out of phase. So you're going to draw from the origin here, from the origin here, you're going to draw your VL. Great, so this is now your VL. Great. Now by the way, if you find this tutorial useful, please make sure you give it a thumbs up and subscribe to my channel. That will be highly appreciated. This is a resistive load phasor diagram there will be a capacitive and inductive load phasor diagram for the short transmission line as well. So please make sure you subscribe so that you don't miss those tutorials. Okay, so we move on here. What are we going to do next? So we've got our VL, we got VR. So the next thing here is to get VZ. But as you can see, VZ have a particular angle here, that is theta Z. And also these VL here have an angle, right? Unlike the VR that got zero angle, it's basically in phase with the receiving end voltage. VL have a 90-degree angle, so we're going to go ahead and place that angle. Now we can draw VZ based on the calculation of VR plus VL. We can then deduce the angle of VZ. So let's go ahead and place the angle of VZ. Okay, so there is the angle of VZ. So this angle here is basically going to be theta Z. Now once we know what is theta Z, we can then, from the origin, based on the value of VZ that we found on scale, right, we assume we are drawing all of these phasors on scale, we can go ahead and place our VZ. Okay, so this is, so thus here is VZ with an angle theta Z. Great. Now that we've got VZ drawn on our phasor diagram here, the next thing is we just need to draw the V sending. Okay, now we know that through the working of this equivalent circuit, V sending here is going to be greater than the V receiving. And why? Because there will be a voltage drop across a transmission line. So if we send 132 kilovolt, we only going to receive, let's say, 131.5 kilovolt. We're going to have a couple of hundreds of volt that's going to drop across R and XL, and that is represented by VZ, okay, that we already draw here. How do we then draw the V sending? Now, since V sending, according to Kirchhoff voltage law, is going to be VZ plus V receiving, so we need to project the VZ. VZ must be projected at the top of V receiving, so that we can then do phasor combinations of this segment of VZ must then be combined with the V receiving to give us V sending. That's basically what we need to do here. Great. So let us now project the voltage across the transmission line to the top of V receiving end. Okay, great. So now you can see that if we now draw, because now we know that we can calculate V sending end by adding VZ plus VR, that will also give us the angle of V sending. So if we know what the angle of V sending, we can basically draw it so that we can know exactly from the origin where is V sending standing. Okay, so let's go ahead and place that angle. Okay, so this is going to be the V sending angle. We can go ahead and place theta sending right here. Okay, so this is theta sending, the angle of the sending voltage. Now we can draw from the origin V sending. Great. So this is it, guys, how you can draw a phasor diagram for a resistive load, right, for a short transmission line, okay, with your impedance parameters. So make sure you join me next time in this tutorial number 2, because this is tutorial 1, overhead line steady state operation. So in tutorial 2 we are going to draw the phasor diagram for inductive load, right, for a purely inductive load, and we're going to finish off with a phasor diagram for a capacitive load. So please make sure you tune in so you can see this here is going to be much different for a capacitive load, because now we're not going to have the current in phase with the receiving end, because here IL is in phase because it's a resistive load. But for a capacitive or resistive load, this current will be either lagging or leading the voltage. So please make sure you tune in for that particular tutorial. Until next time, cheers. Hey there, thank you for tuning into CMTEQ channel in the short series of tutorial on overhead lines parameters calculation. More specifically, in this tutorial, we're going to take a look at how to calculate the resistance per phase of a three-phase transmission line. Now, first thing first, before you tackle this type of problem, you need to understand the problem statement, right? Now, the problem statement states that we need to calculate the resistance per phase of a 30 kilometer three-phase transmission line if the diameter of a conductor is 20 millimeter and the resistivity of the conductor material is 2 to the power negative 8 ohm meter. Now, if you are sitting in an exam class, you will most likely be given a formula sheet table where the formula to solve this particular problem is in the formula sheet. But if you do not know what are the parameters involved, you won't know what is the correct formula to pick. It is for that simple reason you need to understand the problem statement. So illustration is very key in solving this type of problem. So we've got a transmission line. So basically we've got a step-up transformer that is transmitting power over the transmission line. And wherever the power is going, we're going to have a step-down transformer as well. And this transmission line is said to have 30 kilometer length, right? So that is the length. And the material being used for this cable here, it is said to have a resistivity, right, of 2 to the power negative 18. So now this could be aluminum or copper, but we know that there is a resistivity of the material. The material resistivity of 2 to the power negative 18 is very small. So these basically indicate that this transmission line is made of a material that have a very low resistance. Now, this could either be copper or aluminum, as I've said earlier. Now, this is essentially very important for transmission line. Why? Because they will minimize energy loss in the transmission line. And that will basically in turn help improve the efficiency of the transmission line. So overall, selecting material with low resistivity is very crucial for ensuring that the transmission line can carry high current with very minimal power dissipation. Great. Now we also have a diameter of 20 millimeter that is given to us. These play a very significant role in determining the resistance of the transmission line's cable. Now, a larger diameter will basically result in a larger cross-sectional area of your conductor, which will basically reduce the resistance of this cable, allowing for more efficient current flow in your transmission line. So basically what we need to understand here is that in power transmission, using conductors with large diameter is basically important because it helps minimize the power losses due to resistive heating, as we all know. However, there is something you have to understand here, that there is a trade-off. So if your cables are too thick, the cost of installing them also will increase because you need structures that are very stronger to basically withstand the weight of those cables. If you also make them smaller, then they can also dissipate more heat as a resistance will also increase. So you need to balance between larger cross-sectional area or diameter versus the strength of your structure. So that's basically what you need to know in a nutshell. But now let's get going with solving this particular problem here. So we now know that we've got the length, we've got the diameter, and we've got the resistivity of the material. So which means if we use our formula sheet, we can quickly pick a formula based on our given problem statement. The correct formula to use is R is equal to rho times the length divided by the area. But now remember, the units here are the SI units, okay? So which means you need to convert kilometers to meters, which is a SI unit, and your diameter of 20 millimeter must also be converted to meter, which is 0.02 meter. But now, by the way, if you find this tutorial useful, please don't forget to give it a thumbs up and subscribe to CMTEQ channel. That will be highly appreciated. I thank you so very much. But now, when you look at your formula here, you've got
the area that is given here in the formula. But in the problem statement, you don't have the area, you've got the diameter. So now you know your cables, your conductors are of a form cylindrical. So which means you need to calculate the area of a cylindrical given the diameter. So now we know that the area is given by this following formula. So A is basically equal to pi times the radius square. So that's the area of a cylindrical. So now you know what a radius is. A radius is basically the diameter divided by 2. So you can just replace it in this formula here. So you're going to have pi times the diameter divided by 2 and everything square. You're going to have here pi times 0,02 divided by 2. It's basically meter here and square. And you know that the area is given in meter square. So basically your answer here is going to be pi times 10 to the power negative 4 meter square. So this is basically the area of this particular conductor. So now you've got the area of the conductor, you've got the length, you've got the resistivity of the material. So now you can just go ahead and plot in the parameters and you're going to find the resistance of the particular conductors. Now remember, the resistance is given in ohms, so you have to ensure that you can cancel all the other SI unit that does not belong to the final answer. So let's go ahead and solve our resistance. So we're going to have R. So the resistive of the material is 2 to the power negative 8. So it's basically ohm meter, right? Times the length, which is now 30,000 meters. And this is all going to be divided by the area of the conductor, which we then calculated to be equal to pi times 10 to the power negative 4 meter square. Okay, now already you can see that this meter and this meter is going to give you a meter square, and meter square and meter square, they're basically going to cancel themselves here, and you're only going to have a one unit here that basically going to be ohm. So now all you have left is to compute 2 times 10 to the power negative 8 divided by pi times 10 to the power negative 4, and that is going to give you a value of 1,91 ohm. So that basically your final resistance for this problem here, right? So now when you look at it, 1.91 ohm is quite a big resistance if you're going to be transmitting like 2 kiloamps of current. But now remember, this resistance is not over 10 meters. This is over 30 kilometers long of a transmission line that you only going to have a 1.91 resistance across that distance. So basically the amount of power you're going to transmit over this distance versus how much you're going to dissipate, they can actually justify these power losses. So that's basically it in this tutorial. So stay tuned for the next tutorial where we're going to take a look at how to calculate the inductance and the capacitance. Just as you see that we are able to calculate the resistance parameters of this overhead line here, equally so we can calculate the inductance and the capacitors across these transmission lines here. So stay tuned for that upcoming short tutorial. Until next time, cheers.
Hi there, welcome back to CMTEQ channel. In this tutorial 2 of the overhead line steady state operation, we're going to be discussing how to draw this phasor diagram of an inductive load for a short transmission line. So if you want to know how to draw this phasor diagram and get a solid understanding of how each phasor is related to each other here, please stay tuned until the end of this tutorial. In the previous tutorial, we were discussing about the resistive load operation of a transmission line. If you want to know the phasor diagram operation of a resistive load transmission line, please watch tutorial 1. Great. So as we know from tutorial 1 that for short transmission line equivalent circuit diagram like this, the capacitive reactance is negligible, we only focus on the resistive and reactance of the line to basically calculate the voltage drop. So that is given by Z is R plus JXL. Please watch tutorial 1 where we talk in great detail about this equivalent circuit diagram. Great. So to better understand the phasor diagram and draw it accurately for this short transmission line, you need to understand the characteristics of the load. This is why we did for a resistive load where the angle was 0 degree, right? The angle of the current was 0 degrees, so there was no phase angle, okay? But now in inductive load, the situation will change because the load is now purely inductive, okay? Now because the load is purely inductive, the current will then lag the voltage, right? Now this is the Vrec, the receiving end voltage. So the current will lag the receiving end voltage at an angle, which will be a negative angle. Now these lags is basically introduced because of the inductance, the inductive reactance that opposes the changes in current. So that will basically what will give us a negative angle for the current. Now that is a key point you need to understand so that you can start drawing your phasor diagram. Now let's go ahead and start drawing this phasor diagram. Great. So first you need your origin, the starting point of everything. So this is our origin here. Then you need to draw the reference voltage, which is Vrec at 0 degree angle. And we draw our Vrec. Okay. Then because we understand that this is an inductive load and the current lags the voltage at a negative angle, then we can calculate that angle. Okay, once we calculate that angle, we can then plot that angle somewhere here and get the magnitude of the phasor, the current phasor. That way we can then have the phasor of the current drawn at a particular angle. So this here is then the negative angle of the current that lags the voltage, and thus current IL is equal to the I send as we discussed on tutorial 1, because it is a series circuit, so the input current is the same as the output current here, but there is an angle difference between the two because there is an angle that is introduced in the load current. Great. Now the next element for our phasor here, basically the next phasor is the voltage drop across the transmission line, or VZ. Okay, now the same applies with the resistive load here. We know that VR here will be in phase with the current. Okay, so VR will be in phase with the current. We can then draw our VR phasor just like that. But now because VL is basically leading this VR here by 90 degree, it's important to note that this VL here, the voltage across this inductance here, that VL is not leading Vrec by 90 degree. It is leading VR, the voltage across the transmission line resistance, by 90 degrees. So that means we can draw our VL 90 degree out of phase with VR. And by the way, if you find this tutorial useful, please make sure you give a thumbs up and subscribe to CMTEQ channel. That will be highly appreciated. Thank you so much for the support. And if you are studying power system and you'd like to receive assistance from CMTEQ channel, you are more than welcome to join CMTEQ channel membership. And that way you can pose your assignment related question or any other topic you'd like CMTEQ channel to personally cover. So feel free to go ahead and join the channel membership. Great. Now that we know the phasor of VL and we've also plotted the phasor of VR, we can very much easily make an algebraic sum of these two phasor here, okay, to basically make a projection of our VZ. But equally so, if we know the value of VR and the value of VL, we can easily calculate the value of Vz, which is angle, and plot the Vz phasor in reference with the V receiving end, because it is important to note that Vz is the voltage drop on the transmission line that is in reference to the receiving end voltage. So which means the angle of Vz here must be reference to the V reg. So we can go ahead and make a projection of our Vz. That will be the voltage drop across the transmission line, and the angle theta z can then be reference from the V reg phasor. Great. Now to complete our phasor diagram for inductive load here, we only need to draw the sending end voltage, V sending. Now this is here is the power plant, basically our substation or the generating substation, where we're generating the voltage at 132 kilovolt, and we want to send it along the transmission line using these pylon here. Okay, and we encounter a voltage drop across the transmission line because of the reactive element of the cable and the resistive element of the cable. Okay, so now we need to know how much will be our V sending in relation to the V receiving, because remember, V receiving before we close a circuit breaker here is basically equal to V sending. Okay, but as soon as we close a circuit breaker, there is going to be a current flow, then there will be a voltage drop, and V receiving will be less than V sending. So just like we did on the resistive load tutorial, to draw the phasor diagram of V sending, we have to make a projection of the Vz, because remember, what's missing in this V receiving end here is Vz. So V sending end is the algebraic sum of V receiving, okay, plus Vz. That will be the V sending voltage, V drop plus V receiving. So in order to draw it in a phasor diagram, we make a projection of this phasor here. Okay, we project it at the top of V receiving end here, and based on this projection, we can then go ahead and plot the V sending phasor from the reference to the top of this projection here. That will then be the V sending end voltage. Okay, so the V sending end voltage will have an angle theta sending. This is going to be theta sending in reference to the receiving end voltage, and between the load current phasor and the sending end voltage phasor, we're going to have an angle there, and this is basically going to be the total angle between theta send, and that's basically going to be theta L plus the sending end angle. So this is it, guys, for this tutorial on how to draw a phasor diagram for an inductive load in a short transmission line. So if you found this tutorial useful, please make sure you give it a thumbs up and subscribe to my channel. That will be highly appreciated. If you have a comment, please drop your comment in the comment section below. Until next time, cheers.
Hey there, welcome back to CMTEQ channel. This is a second tutorial on overhead line parameters calculation. More specifically, we'll be focusing on how to calculate the inductance per phase of a three-phase transposed transmission line with flat regular spacing. So if you are studying electrical power system or you are working on transmission line design, these calculations is very essential for you. So let's break it down step by step. Great. So first thing first, you need to understand the problem statement. So what is our scenario? So the scenario is very simple. We have a three-phase transmission line that is 50 kilometers long with conductors that are 25 millimeters in diameter. Then we also know that the conductors are suspended in horizontal plane with 1 meter spacing. So what does all of this mean? Before you can actually start solving the problem, you need to visualize your problem statement. Now, transpositions of the transmission line cable here is basically what you see here. So we basically changing periodically the positions of each one of the lines. So the red line, the yellow or the blue line, they're going to be swapping position. Now, this is done to reduce what is known as crosstalk. Otherwise, it is to improve the transmission line efficiency. Now, just as we solved the resistance of the line by calculating the resistance per kilometer, the inductance is also calculated per kilometer given with a general formula that is given by L is equal to 0.05 plus 0.2 times ln the natural logarithm of dE divided by R. So the answer will be in millihenry per kilometer, right? So now if you've got 50 kilometer, then you know whatever answer you get here, you must multiply it by 50 so that you can get the inductance of your transmission line based on the distance where your transmission line is running. But now we've got a few parameters here that we need to make sense of before we can actually calculate these inductance. So the first parameter here is dE. Now dE is related to the conductors that are suspended in a horizontal plane with 1 meter spacing, right? So now if dE is equal to the cubic root of 2d, that basically means your conductors here, like in our cases, they are basically equally spaced. Now, if you have a situation where these conductors are actually not equally spaced, right? So if they are not equally spaced, right? So which means the distance here is not equal to the distance here. In that case, you're going to have dE must be equal to the cubic root of A times B times C, right? That will be your dE in this case. But if they are equally spaced, that basically means you've got D here, that's the diameter, the distance, and you've got another distance here. Then the distance from this point to this point will be equal to this distance times 2. That is why we've got dE is equal to the cubic root of 2d in a case where they are equally spaced. Right now, having said that, we can now go ahead and calculate dE. In this case, it's going to be equal to the cubic root of 2 times 1 because our D here is equal to 1 meter spacing. Then we're going to get a dE of 1.26 meter. Right, now the next parameter here in our formula is the radius. Now this is related to the diameter of the cable or conductor, so we can just go ahead and calculate our radius, which is the diameter divided by 2. Then we've got 25 millimeter divided by 2, and we find the radius of 0.0125 meter, right? So we have to convert the millimeter to meter for the SI unit, just as we have dE here in meter. Great. Now, before we complete this calculation, if you find this tutorial useful so far, please make sure you give it a thumbs up and subscribe to CMTEQ channel so that you don't miss more tutorial of this nature. Now, it is also important for us to know the meaning of this calculation. Why do we have to actually understand? Why do we actually need to calculate the inductance of the transmission line here? Now, the answer is very simple. As I've said earlier, this is crucial for the design and operation of the transmission system, as inductance basically directly affects several key factors in power delivery, right? Now, these key factors, just like with the resistor, the inductance can also affect the voltage drop, power losses, and more importantly, impedance matching, right? Impedance matching in transmission line is definitely important. Proper impedance matching is important for power system stability, and that will ensure that we avoid excessive voltage drop or voltage surges in the power lines. And a few other reasons are power flow control, voltage regulations, and system stability, as I've said earlier. So that is why it is very important to know your line, your overhead line parameters. Right, now let's continue our calculation here. So after you've calculated your radius, all you have to do next here is to basically replace your calculated dE and your calculated R into your main formula for your inductance parameter. That will basically give you the following equation here, where you can calculate your inductance per kilometer, right? So this gives us a value of an inductor of 0.973 millihenry per kilometers, right? So now, based on what's given to us here, 1 meter spacing between A, B, and C, and a 25 millimeter conductor's diameter, we now found an inductor of L is equal to 0.973 millihenry per kilometer. Now, this basically tells us that if you're going to have this kind of configuration structures, that's the inductors that you have. So now, if your line is now going to run for 50 kilometers, all you have to do is to basically multiply the calculated inductors times 50 kilometers, right? So that would basically be L is equal to 0.973 times 50 divided by kilometer millihenry per kilometer. Now these will basically cancel the kilometers here, and you're gonna have a final inductance value of 48.63 millihenry for these line parameters here. Now imagine you are a power system transmission line designer, and you've been given these specification for the line, and you've calculated your inductance per kilometer to be 0.973, and for a 50 kilometer you are projecting to have an inductance on your line of 48.63 millihenry. Now you know that transmission lines sometimes they run for longer than these hundreds of kilometers, so which basically means this inductance is bound to increase the longer you take your lines to. Now what are the implications of these inductance? As we've already stated earlier, some of the implications are harmonics, distortions, and power quality, right? So inductance, they will contribute to harmonic distortion in your power system, which will basically affect the quality of the electricity that you are basically transmitting, right? Now, knowing these value, it will help in terms of improving the design. So you can basically include some series capacitors. The addition of series capacitors or shunt reactors will actually act as compensating devices in your transmission line to basically maintain the voltage stability. So that is very important to take in note as power system designer. Thank you guys for watching. I hope this tutorial was useful. If you find it useful, please make sure you give it a thumbs up and subscribe to CMTEQ channel for more tutorial of this nature. Next up, we're going to have a tutorial where we're going to see how to calculate the capacitance of a transmission line. Until next time, cheers.
Hey there, welcome back to CMTEQ channel. This is tutorial 3 on overhead line steady state operation. In this tutorial, we'll be discussing the capacitive phasor diagram. So if you'd like to catch up on the previous tutorial on resistive and inductive phasor diagram, please watch tutorial 1 and 2, link in the description box. But before we move on with this tutorial, I'd like to clarify a few things based on the discussion on CMTEQ channel community posts. Great. So first off, this tutorial is based on the transmission of AC power. This is why we are discussing phasor diagram, phase angle, and so forth, because in DC power transmission you will not have phase angle or phase shift. And why AC power transmission? Well, because we're discussing power system steady state operation, and as we all know, all power system network transmission line around the world, I can safely say they are all done in alternating current, not in DC. And obviously this particular circuit can be analyzed in context of DC analysis. If you plug in a DC power source here, you can run a transient or steady state operation of this particular circuit based on the resistive, capacitive, and inductive load. But that is not what we're doing here. We are analyzing a power system transmission line operation, which is done in AC power, alternating current. And that is the case because Nikola Tesla, about 110 years ago or so, won the argument against Thomas Edison on why use AC instead of DC, because Thomas Edison was pushing the argument about DC power transmission, DC system, because at the time Thomas Edison had lots of argument and invention around the DC power system, while Nikola Tesla was doing experiment and inventions around AC power transmission. So at the end of the day, what was known as the war of current was eventually won by Nikola Tesla. This is why today we're transmitting our power using alternating current. Although Nikola Tesla won the war of currents and we transmit power using AC, we still convert it back to DC for everyday use. So you can basically look around you when you plug your instrument, your tools, or your cell phone to a wall adapter. You basically have a charger that will convert AC power back to DC for everyday use. So in the end, Thomas Edison, he had a point, but it is practically impossible to transmit power efficiently in DC over a long distance. Well, that was the argument there, and maybe that argument is not so strong today because the DC power transmission is coming back slowly, not at the same level as AC power transmission is today. But as technology evolves, we will start seeing DC power transmission gaining more and more prominence in power system technology. But that's a subject for another tutorial. Let's get back to our steady state operation for transmission line running at 50 or 60 Hertz frequency, because this circuit will also behave differently if you have a voltage source that is running at a higher frequency, right? So that will be very different if you supply a PWM signal at 100 kilohertz or 1 megahertz or so forth. Then the behavior will be very, very different here. But now we are running at low frequency because the inductance as a load, the impedance will be different depending on the frequency, okay? And the same applies for a capacitor. Now, as we all know, the inductive reactance and capacitive reactance, they depend on the frequency of operation of the circuit in which they are operating, okay? So in the case of XL, we know that XL is equal to 2 pi FL, okay? Where these inductive reactance will depend on the value of the frequency and the inductance. Now, if the inductance got a fixed value, then at high frequency, then this impedance is going to be high, okay? And at low frequency is also going to be low. This is why in an AC circuit like this with 50 Hertz operation, your inductance will initially won't behave exactly like an open to affect the opposition to the current, right? There will be some current that will flow because of the low impedance that is dependent on the frequency of the transmission line. The inductance will allow more current to flow in the circuit, with the current basically lagging the voltage by 90 degrees as we've seen in the previous tutorial. But now in the case of a capacitive load where XC is equal to 1 over 2 pi FC, right? In this case here, the capacitive reactance also depend on the frequency and the capacitor, obviously. Now, if you've got a fixed capacitor, then a low frequency of 50 Hertz here is going to basically result in a high capacitive reactance. Compare if you have a high frequency circuit, then your XC, your capacitive reactance, is going to be low if you have a high frequency. Right now here, we're going to be dealing with a system that got a purely capacitive load. In that case, we're going to be having a situation where the capacitive reactance is going to be significantly high, depending on the value, obviously, of our capacitor, because our frequency is now fixed at 50 Hertz. So in a high frequency situation, the capacitive reactance will be extremely low, and as a result, this capacitor will initially behave like a short. But in a low frequency system like this transmission line, the capacitive reactance is going to be high, and based on this, there will be some current flow to try to charge this capacitor, and this current will basically going to lead the voltage by an angle of 90 degrees. So we're going to have a positive angle of the current compared to a lagging current in an inductive case. So this is basically the difference between the two, relating to whether you are supplying a low frequency or a high frequency signal. Great. Now before we move forward, please, if you find this tutorial useful, please make sure you give it a thumbs up and subscribe to CMTEQ channel. That will be highly appreciated. And also, if you'd like to join this channel membership to receive assistance for your assignment, homework, or project, or whatever you are dealing in your electrical engineering journey, CMTEQ channel will be here to assist you. Great. Now we know that for a capacitive load for our short transmission line operation here, we know that the current, the load current here, IL, is going to be leading the voltage by an angle here. So it's basically a positive angle. So we can now use this information with the information that we already know about the voltage drop across the transmission line. Okay, we can now draw our capacitive phasor diagram. So the solution to this question is very simple. We're going to start by the reference voltage, which is basically V rec here with an angle of 0 degree before the circuit breaker is closed, because everything we basically discussing here will only take place after the circuit breaker have been closed. Okay, so for a reference V rec with an angle of 0 degree, we now know that once the circuit breaker is closed, there will be a current that will basically lead the reference voltage by an angle. So let's go ahead and draw that angle. This is an unknown angle. We can calculate it if we've got the values. Okay, now that we know where the location of that angle is, we can then calculate the magnitude of our current, of the load current. Okay, then we can go ahead and draw the load current phasor. Okay, now we've got the load current phasor, which is leading by theta L, the reference voltage V rec. Now, once the circuit breaker have been closed and we've got the current that's leading the voltage by an angle, the next thing that will happen, there will be some situation that will start to develop here at the transmission line. Right, the first situation will be VR, the voltage across the resistance of the cable, is going to be in phase with this current IL, which is the same current as I send. Okay, so that voltage will be in phase with IL, that will be VR. Okay, and we also know that there will be another voltage that will develop across XL, the inductive reactance of the line, and that voltage is going to lead VR here by an angle of 90 degrees. And the algebraic sum of these two phasors, VL and VR, that basically what would be our VZ, the voltage drop across the transmission line VZ, and this voltage drop has an angle theta Z that we can actually calculate and reference here to draw the phasor of VZ at theta Z. Okay, so this now will be VZ, basically the voltage drop across the transmission line. But now we are almost done with drawing our phasor diagram. The next thing we need to do is now to make a projection, or to basically draw the sending end voltage, because we've got the receiving end voltage, which is V rec at a reference of 0 degree. Now we need the sending end voltage. We know that the sending end voltage is going to be slightly higher than the receiving end voltage. This is because of the power loss across the transmission line. So there is a voltage drop across the transmission line. That voltage drop must be deducted from the sending end voltage to get the receiving end voltage, V rec. Now if you want V send, then you can just add the V rec, V receiving, plus VZ to get V sending. So now we got V receiving here that we've already plotted, and we've got the VZ here. So we can just make a phasor sum of these two here by making a projection of VZ to the top of V rec here. Okay, so to do that, we're going to make a projection. Okay, now we've done the vector sum of V rec vector and VZ vector by combining them at the end of one another. Now even without drawing the angle of V sending, theta sending, we can already make a projection where V sending is going to end. It's going to end there, and that will already determined the angle theta send. So this here will be V sending, basically the sending end voltage. And over here, basically the angle between the sending end voltage and the load current, that angle can also be calculated. That basically going to be theta L minus the sending end angle. Then you're going to get this angle. Great. So this is it, guys, for this tutorial on how to draw the phasor diagram for a short transmission line in steady state operation. So tutorial 1 we did for resistive load, tutorial 2 for inductive load. Now we're closing this series with capacitive load. So I hope you found it useful, and if you have, please make sure you subscribe to CMTEQ channel and give this tutorial a thumbs up. Stay tuned for more tutorial on AC power transmission line analysis. Until next time, cheers. Hey guys, welcome back to CMTEQ channel. In this tutorial 3 on overhead line parameters calculation. In tutorial 1 and 2 we saw how we calculated the resistance and the inductance of a transmission line. In this tutorial we're going to look at how to calculate the capacitance of an overhead transmission line. So basically the problem statement is that the power system designer is planning to set up a 50-kilometer three-phase transmission line using conductors with 20 millimeter diameter and spaced 1 meter apart, so that basically the distance between the conductors, as we've seen in the previous tutorial. Now the 3 questions that we need to deal with is that we need to calculate the per phase capacitance, the line-to-line capacitance, and the three-phase capacitance with a symmetrical spacing of 1 meter between the line. Now before we start solving this problem, let's first look at where these capacitance that we're going to be solving here are coming from. Right now, as you can see here, we've got phase 1, phase 2, phase 3, and we've got capacitance here and another capacitance, and there is also a capacitance here between the ground and the phase. Now this one here is rather a small capacitance because of the distance, right, the height where our conductors are actually situated, right? Now assume this is our transmission line here, so we're going to have a capacitor here and another capacitor is also going to be here, right? These are our 2 capacitance, right, between the line and the phase and the overall 3-phase capacitance. So what causes these capacitance? Now it's very simple, right? So in the overhead transmission line, basically this capacitance is simply the ability of this line here to store electric charge between the conductors, as you can see. But now the storing of this electric charge is caused by a few other factors, one of which is the permeability of the free space that basically will be our dielectric here that will cause that capacitance, and also the geometry of this line here, right? So that will be the distance between these conductors. Now here on our problem, we have been told that the distance is 1 meter apart, right? So that will be part of what will cause the capacitance, as we'll understand that the closer they are, the bigger your capacitance is also going to be, because there will be a higher concentration of that electric field. So in a nutshell, these capacitance arises due to the potential difference between these conductors and the surrounding environment, which would basically form part of a weak electric field. Now, having said that, capacitance is a key factor in the overall behavior of a transmission line, affecting its charging current, power loss, voltage regulations, and system stability. As it is quite evident that these capacitance will play a very crucial role in long distance transmission line, especially in high voltage transmission line, as we're going to see when we start calculating the transmission line calculations, pi methods, and so forth. Now let's go ahead and start solving our problem statement here based on the parameters given to us. So now we understand that we've got the diameter of our conductors that is standing at 20 millimeters, which means we're going to have a radius of 0.01 meter. And the next parameter that we need to understand here is also the permeability of the free space. Right now, remember when we talk about the dielectric of the capacitance, right? So this capacitor here
the dielectric material is basically the vacuum, is air, right? So the free space. So which means we need to make use of the permeability of the free space here so that we can get our calculation right. Great. Now the next parameter is obviously the length of the line is 50 kilometers and the spacing or the distance between the conductors is 1 meters. Right. Now the first question is the per phase capacitance. Okay, now before we continue, please, if you find this tutorial useful, please make sure you give it a thumbs up and subscribe to CMTEQ channel. That will be highly appreciated. I thank you so very much. Now, to calculate the per phase capacitance of a transmission line, let's consider we've got phase A and phase B, and we've got a neutral wire here. So that basically means we're going to have a capacitor between a neutral and phase A and between neutral and phase B. Now, if the distance between these two phases and the neutral is basically equal, spaced at 1 meter, that basically means the per phase capacitance must be this capacitor times 2, or this capacitance times 2. This is why this is given by the following formula. And here, D is the distance between the conductor and R is obviously our radius here. And once we know all our parameters, we can basically go ahead and calculate our per phase capacitance here. And that will be given as the C per phase is 1,21 times 10 to the power negative 11 farad per meter. But now, our problem here is to calculate the capacitance per phase for a 50 kilometer line. So which means we need to multiply this entire value here by 50,000, and that will basically give us the value of the capacitance per phase for a 50 kilometer line to be equal to 0.605 microfarad. That basically make more sense to us. Right now, let's go ahead and calculate the line-to-line capacitance. To calculate a line-to-line capacitance, it's very simple here, because now consider that we've got our two conductors here, phase A and phase B, and this is our capacitance. Now we don't have a neutral line anymore, so that basically means the capacitance is only this one capacitance here. So what does this mean? So we can basically just take the value of what we calculated on the per phase capacitance, we divide it by 2, and that will just give us our line to line capacitance. Okay, so that will just be line to line capacitance is equal to the C phase divided by 2. Okay, and that will basically be 0.302 microfarad. As simple as that, right? Now let's go ahead and calculate the three-phase capacitance of an overhead transmission line. Now this is where it gets quite interesting. Now let's consider this is our three-phase, right? So which basically means we've got C1 here and we've got C2 here, right? So if we want to calculate the three-phase capacitance with 1 meter spacing between these conductors here, we basically have to add these two capacitance. Basically, if this distance and this distance is equal, we're basically going to just say to get the capacitance of this line, we must just multiply this capacitance by 2, because this capacitance and this capacitance, they are basically equal. It's basically the same thing that we've done here when we calculated for a single phase. But now the trick here is that because this is now for a three-phase asymmetrical, we need to take care of the distance between all three conductors, okay? Considering also the distance between this conductor here and this conductor here, okay? And having said that, the formula to calculate the three-phase asymmetrical capacitance of an overhead line is basically equal to 2 pi epsilon divided by the length of DE over R, and DE here being equal to the cubic root of 2D, which is basically taking care of the distance between the conductors. Right now, we already talked about this equation here on tutorial 1 and 2, basically on tutorial 2 when we talked about the inductance of an overhead transmission line. But now it is important that you note that this particular formula here, the way we've solved it here, is for symmetrical spacing, where we've got this distance and this distance, they are basically equal 1 meter. But if you have a situation where the distances are basically not equal, you might have 1.5 meters or 2 meters on the other side, then you need to use this particular arrangement to basically get your correct value of DE. That is a very key point to actually note, that here we are basically calculating for symmetrical spacing, not asymmetrical spacing. Right, so now we can go ahead and plot in our variables here, because we know what is our DE and what is our radius here, and that basically give us a three-phase capacitance of 1,14977 10 to the power negative 11 farad per meter. As always, we need to multiply this by 50,000, basically 50,000 meters, so that we can get a capacitance of this 50 kilometer line. So that basically gives us an overall capacitance of 0.575 microfarad. As you can see, the three-phase capacitance is very much close to the per phase capacitance when calculating between the phase and the neutral. And that is basically it for this tutorial. Thank you guys for watching. If you find it useful, as always, please give it a thumbs up and subscribe to CMTEQ channel. Until next time, cheers.
Hey there, welcome back to CMTEQ channel. In this tutorial, we're going to cover one of the typical problem in electrical power distribution, where power system engineers or students usually are tasked to find the value of the voltage at the sending end, the regulation of the line, the efficiency in a short transmission line. Now, a while back, I did a series of tutorial where we discussed a steady state operation and drew a phasor diagram for a short transmission line with either inductive, resistive, and capacitive load. I really recommend that you watch those tutorials if you want to understand how a short transmission line basically operate. So without any further ado, let's get started and determine the value of the voltage at the sending end for this transmission line. Now, the first thing you need to imagine here, this is a three-phase system. This means that if your transmission line is configured in a star configuration, you're gonna have a 4-wire system: line 1, line 2, line 3, and the neutral point for your transmission line. So it's always important to visualize what you are trying to solve, because good illustration always make things easier to solve and understand the problem statement. So here we've got a three-phase system. Okay, so at the sending end here, this is your typical power plant and your three-phase star connected transformer transmitting via RYB, line 1, line 2, line 3. And at the receiving end, you've got the same scenario with your three-phase transformer. So now we need to find the voltage at the sending end. Okay, now the voltage at the sending end that we need to determine here, it could either be the line voltage or the phase voltage, because there are three phases here, and the same applies at the receiving end. But now the voltage at the receiving end is subject to the voltage drop across a transmission line, which is your VZ, based on the line impedance. Now in the problem statement, we've got a 5 ohm resistance per phase and an inductive reactance per phase of 12 ohm. Right now, the system at the receiving end is basically running at a 20 megavolt ampere of power with a lagging power factor of 0.8. Okay, so the line voltage at the receiving end is 33 kilovolt. Now these type of problem, they basically solve with the per phase parameters. You need to solve it per phase, because if we assume it is a balanced system, then there is no need to really solve it for a three-phase configuration, because all the values are going to be the same for each phase, assuming it's a balanced system. So we work out a single line diagram for a single phase so that we can solve our problems. Okay, so to do that, we draw the single line diagram here, and we end up having a similar diagram that we were analyzing when we drew
the phasor diagram for the short transmission line. Now, according to the problem statement, this particular resistance value is 5 ohm, and this inductive reactance is also a 12 ohm J per phase. Now, when the switch is closed, you're going to have a voltage here at the receiving end, and that is known as V receiving. Okay, and at the sending end, we also have a voltage that we call as V sending. Okay, now across the line, we've got a voltage drop that is caused by the impedance of the line, and that voltage is known as Vz. Now, the question here is to find the voltage at the sending end, but we are only given the voltage at the receiving end, which is also given as a line-to-line parameters, okay? But now we're working with the phase parameters, okay? So we need to find the phase voltage at the receiving end. But first, the formula to find the voltage at the sending end is basically the voltage at the receiving end plus the voltage drop across the line. But what is the voltage at the receiving end per phase? That basically this voltage divided by the square root of 3. It's as simple as that. So we find a value of 19.05 kilovolt per phase. So basically each one of these phase here is carrying a voltage potential of 19.052 kilovolt. Now the next stage is now to basically calculate Vz. Since we now know what is the V received per phase, if we find Vz, we will know what the voltage at the sending end is. So how do we calculate Vz? Now this is very simple. Vz is equal to I phase times the Z per phase. Now we already have the Z per phase here. Based on the resistance and the reactance per phase, we can find the Z per phase. Now, what is the value of the current per phase? Okay. Now, to find the current per phase, we're going to use the formula of the apparent power. Since we are told that the system at the receiving end is using about 20 megavolt ampere of power at a lagging power factor of 0.8. So which means using this formula, we can deduce the value of the line current, okay? Because remember, this is a series circuit. So the current flowing here, I line, is the same current that is also flowing here, okay? Now, based on that, we can say that the line current is S at the receiving end divided by the square root of 3 times V at the receiving end. Remember, that must be V line at the receiving end, not the per phase voltage. Okay, so by the way, if you find this tutorial useful, please make sure you give the thumbs up and subscribe to CMTEQ channel. That will be highly appreciated. Thank you very much for the support. Great stuff. Now continuing, we can calculate the I line by simply doing 20 MVA divided by the square root of 3 times 33 kilovolt. That will give us 350 amps. Great. Now it is important to understand that in a star configuration, I line is the same as I phase. Now a quick illustration, we're going to have a star configuration that look like this. So this is your neutral point. So this is your line 1, I1, and it's the same current that's flowing there. And here we're going to have I2, and it is the same current that's also flowing there. And here you're gonna have I3, okay, and it is also the same current. Now these are your phases, okay, these are your phase, okay. So that phase 1, phase 2, phase 3, and the current flowing onto the line is exactly the same current flowing into the phases. This is not the case in a delta configuration, so it's very important to understand that. Great. Now that we know what is the line current or what is the phase current, we now need to know the angle of this phase current. Since the problem statement states that there is a power factor of 0.8 lagging, so which means the current is basically behind, the voltage is leading. Okay, so how are we going to determine the angle of this current is very simple. So cos theta here is 0.8. That means we can find the angle by taking the inverse cos of 0.8, which gives us 36.87 degree of angle. Okay, now since it is lagging, then we have to assign a negative sign to the angle of the current because it is lagging behind the voltage. Great stuff. Does then mean that our line current or our phase current is 350 with an angle of negative 36.87. Now the only ingredient that we need here to calculate our VZ here is the impedance. Now we know that we got 5 ohm and 12 ohm for the reactance. It's very simple. We can calculate this impedance since it's given in a rectangular form. We convert it in a polar form simply by using your calculator functions. You can convert it very easily. Okay, now after that we can then combine VZ is the current times the impedance, and we find a voltage drop on this transmission line per phase of 4550 volt with an angle of 30.51 degree. Now this is basically 4.5 kilovolt. Now we now have everything we need to calculate the voltage at the sending end, which then will be given by the per phase voltage 19.052 plus 4.55 with an angle of 30 degree kilovolt. Now very important, the voltage at the receiving end have an angle of 0 degree, and after working it out you find a per phase voltage at the sending end of 23.088 kilovolt with an angle of 5.74 degree per phase. Great stuff. Now the next thing that we need to do, we now solve our first question. We move to the second question, the line regulation. Now this is very important because if your line regulation is bad, that means you need to fix your system. Okay, the line regulation basically determine how consistent your voltage is at a receiving end, which means you need a smaller percentage line regulation, okay, so that you can actually be satisfied. But now to calculate the line regulation, you have to use the line voltage. Okay, now we already have the voltage at the receiving end line given to us there. Now we just need to convert the voltage at the sending end per phase to a line parameters. That basically just means by multiplying it to a square root of 3, then we're going to have 39.98 kilovolt, basically 40 kilovolt line to line at the sending end. So that basically means if you measure here across these line 1 and line 2, you're going to get about 40 kilovolt in this current configuration. Okay, that means number 2, the line regulation is V sending line minus V receiving line divided by the V receiving line, and that basically means 39.98 minus 33. So we have a line regulation of 21.1%. okay, now this is a percentage value, so you have to multiply it by 100, which we did not specify in the formula. Great stuff. Now the last question in our problem here is the efficiency of the line. Now this is very simple. As we all know, efficiency is by just dividing the receiving power by the sending power. Okay, so that means P receive divided by P sending. That will give us our efficiency, and we must use line parameter to do that. So we got the square root of 3 times 33 kilovolt times the current, the magnitude of the current here, 350 times the power factor, which is 0.8. okay, so that is what we have at the receiving end. Now what is the power at the sending end? The power at the sending end is the square root of 3 times the 39.98 kilovolt times the magnitude of the same current, because remember the current here is the same current that you see at the receiving end. Okay, then the angle, very important here. Okay, so you have to subtract the angle that you get from the sending end voltage that you calculated, this angle here per phase. You must subtract the angle of the current, okay, because that's the current at the receiving end, because the angle of that current is determined by the power factor at the receiving end. So you subtract that, that will basically give you a different power factor at the sending end, and that will determine your power at the sending end, and this will basically be 16 megawatt at the receiving end divided by 17.84 megawatt at the sending end. So you can see that we've got some power that is dropped across the line. So your efficiency of the line is 89.69%. Now this is a very typical problem. This is a very simple example. There are ways in which certain questions can be framed and asked, where if you understand how all these parameters interact with each other based on the phasor diagram, you will get it. But if you do not grasp that properly, you will find it very difficult to solve some of the question if they frame it differently. So stay tuned for the next tutorial, where we're going to be doing some advanced tutorial in these topics. Until next time, cheers. Hey there, welcome back to CMTEQ channel. So this is tutorial 2 on our transmission line calculation. So in this tutorial, we're going to use a nominal pi model to solve this particular problem, where we've got a 3-phase transmission line that supplies 30 megawatt of power with a star connected load, and the line basically at the receiving end is 33 kilovolt with a power factor of 0.7 lagging. Now the line constant basically per phase parameters of the impedances and capacitance, because this is the nominal pi model. Let me just bring the circuit here for this pi model. So we've got capacitors represented at both ends of the circuit, basically at the sending end and at the receiving end, with our series impedance of the transmission line. Now this is a single phase representation of this pi model. Great stuff. Now before we start solving this problem, let's first answer this very basic question: why do power system engineers use the nominal pi model to solve transmission line problem? Now the answer is very simple, and you have to pay attention. This is because this model or method is widely used because it's effectively represent both the series impedance of the line and the shunt capacitance at both ends of the transmission line. Okay, so making it suitable for medium length transmission line of typically 80 to let's say 250 kilometers. Okay, now the model simplifies the analysis by lumping the line's parameters into manageable form without sacrificing the accuracy of your calculations, so which indeed help in calculating voltage drops, power flow, and the system stabilities, which we're going to see in a moment. The main advantage here is that it captures the essential electrical characteristics with fewer calculations compared to a more complex distributed models. Okay, so offering a good balance between simplicity and precision for practical engineering problems. That's what we're going to see in a moment. So now, without wasting any further time on this, so let's start. So this is going to be a step-by-step problem solving strategies here. The way you do it is very simple. First, you need to understand what you've been given to you. Okay, here I've already simplified it for us to represent the different currents in our circuit. So we've got the sending current, and we've got the current through these capacitors. I've named it I2, and the line current I3, and we've got I1 through this the receiving end capacitance, and IR, which is a current at the receiving end. So now the question for us is to solve for the voltage, current, and power factor at the sending end. And obviously, once you've got that, you can solve the efficiency of the line by simply dividing the power at the receiving end, which is 30 megawatt, by the input power. It's as simple as that. Now, let's assume that you are sitting in an exam class and you've been given this power system problem. So the first thing, obviously, you need to read the problem statement, understand it very well, know the given data and what's missing so that you can answer the question. So here, our given data, very simple. The first one is active power. Now, this power is at the receiving end, okay? Then it is at a power factor of 0.7 lagging. That means the angle is negative 45.7 degree. Next is the receiving end line voltage. This is 33 kilovolt. It is being given here. Okay, the next parameter is the impedance per phase. So we've got 30 ohm and 40 ohm for the reactance. That means our Z per phase can be calculated here as 50 the magnitude with an angle of 53.13 degree. Now the impedance here has been given in rectangular form. Then we convert it to polar form because this helps us with the calculations and it's prevent you from making mistakes. So to do that, you grab your calculator. Make sure your calculator is in complex mode, okay? So you go on mode setup, number 2. That means you are in complex, okay? Then you enter your resistance here. It's 30 plus your reactance, which is 40 ohm, okay? 40, then 40J or 40I, okay? Then you just hit equal. Now, that basically you've entered your impedance in a rectangular form. Now you're going to click on Shift to now convert it in polar form. And you're going to hit complex. Then you're going to select number 3. Okay? And then you say equal. Then we basically have 50, the magnitude, with an angle of 53.13 degree. Now, this is what you need to do for all complex calculations because these makes it shorter and it prevents you from making mistakes. If you're going to do calculation using the rectangular form, you're going to do a lot of cross multiplications and you might make mistakes. Great stuff. Now, having said that, we can continue with our parameters here. So we got the shunt reactances, basically C1 and C2, they both minus 800 ohm. That basically we've got 800 with an angle of negative 90 degrees because it's purely capacitive. Great stuff. So first step in order to solve this problem is to convert the line voltage into a phase voltage. So our line voltage here is 33 kilovolt. So we're going to convert 33 kilovolt into a phase voltage. That's very simple. We simply divide it by the square root of 3. So we got 19.052 kilovolt. Second step is we calculate the current at the receiving end. Now this is this current here. Okay, so that's the current that's flowing into the load. This is our load. Okay, in order to calculate the current at the receiving end, you need to see what you've been given. So we've got active power, okay, already stated here. Then we've got a power factor, so you can use the power formula to basically calculate your current. So you can deduce. By the way, if you find this tutorial useful, please make sure you give it a thumbs up and subscribe to CMTEQ channel. That will be highly appreciated. Thank you so very much. And also, if you are preparing for your power system exam or you have an assignment, if you would like to receive assistance from CMTEQ channel, you are more than welcome to reach out. And you can also join CMTEQ channel membership. That way you can make tutorial requests and specific requests for your particular problem. Thank you so very much for assistance. Great stuff. Now, using the power formula, we can simply deduce that IR is equal to PR divided by the square root of 3 times VR times cos theta. Okay, PR, we know that is 30 megawatt, and we can find the magnitude of the current at the receiving end here to be 749.8. But now wait, this current must have an angle because they say the load here, okay, has a power factor of 0.7, which is lagging. We know that the angle between the voltage and the current is negative 45.57 degrees. So we simply going to state that our current is 749.8 with an angle of negative 45.57 degree. Then we continue step 3. Now we have this current. Okay, remember we need to find the voltage, current, and power factor at ascending end, which means we are looking for this voltage. We don't have this voltage, we don't have this current. Okay, so how we get them is by working backward. That is exactly what we're doing. Great. Now we've got this current, the current at the receiving end. Now we're now aiming at the line current, but before we get there, we need to find I1, because I3 is basically I1 plus IR. Okay, now we know that to find I1 here, the current through this capacitance, the shunt capacitance, we need to find the voltage across this capacitance. Now this is where it gets tricky, because this is a parallel. This capacitance is in parallel with the load here. But now we got the current using the line voltage, which is 33 kilovolt. Okay, but now if you use this line voltage to find the current through this capacitance, you going to get it wrong, because this is a single phase diagram. Okay, so these are per phase parameters, so you must use a per phase voltage to find the current through I1. This is why we converted the line voltage here to a phase voltage. Okay, but now why didn't we use the same phase voltage to get IR? Because IR in a star configuration, IR is the line current is equal to the phase current. Is basically the same. I explained it in the previous tutorial. So we have to use now the phase voltage to find I1. Okay, having said that, the formula is very simple. IC1 is VR phase divided by XC1, and that basically gives you 23.81 with an angle of 90 degrees. Now this also you're going to do it very simple using the calculator, just as I've shown earlier. Now we move on. Step 4. We now need to find I3, the current through the series impedance, basically the transmission line current. Now this becomes very simple. We're simply going to apply Kirchhoff current law here. So the sum of current leaving the node is equal to the current entering the node. So I3 here is entering this node here, okay, while I1 and IR are leaving the node. So simply I3 is I1 plus IR, and that basically is going to be equal to these two current added together in this form, okay, basically in polar form. You can also do this with your calculator. Very simple. If I may just show it quickly here for those who would want to know. So it's 749.8 shift, and we enter the angle negative 45.57 plus 23.81 shift with an angle of 90 equal. Okay, now the answer is by default in rectangular form. Now we're going to go shift to get our answer in polar form, 3 and then equal, and that's the answer. So we have a current of 732 or 33 with an angle of negative 44. So that basically the current through the transmission line. Now we move on. Step 5. Great stuff. Now to find the voltage drop across the transmission line, this is very simple. We now know the current or the line current here. Okay, so we are simply going to multiply the line current times the impedance of the transmission line per phase. Remember, okay, per phase parameters, and this current is also a per phase current because the per phase current and line current are the same in a star connected system. Okay, so having said that, Vz is I phase times Z phase. That means it's 50 with an angle of 53 times 733 with an angle of negative 44.3, and that basically gives us this voltage, a huge voltage drop of about 36.6 kilovolt with an angle of 8.8 5.86. Okay, now we know what this voltage is. Now before we can find this current, okay, we first need to find the sending end voltage, and we're going to do that by adding this voltage, okay, plus the voltage at the receiving end. But we're not gonna use the 33 kilovolt, we're going to use the phase voltage because we're working with per phase parameters. Okay, so that will be step 6. The voltage at the sending end is basically V send is equal to VR theta plus VZ theta per phase parameters. Never forget that. So it's gonna be 19.052 with a 0 degree angle with plus 36.6 kilovolt with an angle of 86. That's given to us here, and that means the sending end voltage for this system is 55.5 with an angle of 5.83 degree kilovolt. Now this means we now know what is the voltage across the shunt capacitance at the sending end. It is exactly the voltage at the sending end. So we can now calculate I2 using that voltage. Remember, this is a per phase, it's not a line voltage, it's a per phase voltage at the sending end. Obviously, if you want to calculate a line voltage at the sending end, you must just multiply the 55 times the square root of 3, then you're going to get this voltage that is at the sending end. And you can see the difference between this voltage and this voltage. That tells you how much voltage drop you have across this transmission line. Okay, moving on, step 7. Now in step 7 here, we're going to apply the same formula used in step 3. Okay, this time around we're now going to use the voltage at the sending end, the per phase voltage that we just calculated here, 55.5, to basically get I2. Okay, so that will simply be 55.5 divided by the 800 XC. Okay, so that will give you a current of 69.4 with an angle of 95.8 degree amp. Okay, now once you have this current, you're going to apply the same Kirchhoff current law that we applied here at this node. You're going to apply it at this node here, okay, by simply doing IS here is equal to I2 plus I3. Okay, so that will basically give you the current at the sending end of the line, which is the same as a phase current at the sending end of the line. That is your I2 plus I3. So this is I2 and that's I3. Now once you find this current, okay, then obviously you're going to use this current to calculate the power at the sending end. The same formula that we use here to find the current at the receiving end, this current, now you're going to make PS here. It will now be PS as the subject of the formula. That will now be the square root of 3 times Vs times cos theta times Is. But remember, there is a trick here in finding the power factor at the sending end. You need to add the power factor of the sending end current. So let me know in the comment section if you're going to get it right, because after you find the power at the sending end, you can then take the power at the receiving end here of 30 megawatt. Okay, you can then divide it with the power at the sending end. That means you're going to get your question number 2, the efficiency of the line. So I'm going to stop this here. If you attempt to get that final efficiency, let me know in the comment section. So if you find this tutorial useful, please don't forget to give it a thumbs up, share it to your social media network. Until next time, stay tuned to CMTEQ channel. Cheers. Hey guys, welcome back to CMTEQ channel, where we make power system concepts simple and accessible for everyone. In this tutorial, which is tutorial 3, on our series of tutorial on transmission line calculations, we're going to dive into the nominal T model. Well, why the nominal T model? Well, when you look at this transmission line pylon here with 3 wire, basically 3 conductors, line 1, line 2, line 3, we've got the representation of C1, C2, which are capacitance of the line. Now, the capacitance here in the transmission line is inherent to its physical construction, okay? It naturally exists between the conductors and the ground due to the separation, like the distance between this line and the physical properties of the insulation and so forth. Now, in reality, this capacitance is basically distributed continuously along the length of the line. So you're gonna have another capacitor here, you can call it C3, and here you can call it C4, and these will go all the way for your medium transmission line 250 80 kilometers, right? Now, here is where the problem is. For calculation purpose, especially in medium length for 80 to 250, you cannot ignore line capacitance. For simple short transmission line, you can actually just ignore it and just model it as a series impedance of the line, like in the first tutorial. But for medium transmission line, you cannot ignore the capacitance of the line. So what do engineers do? They try to make things simple. So they create model. Okay, so we've got the pi model, which I've done on the previous tutorial, and this is the nominal T model. This model is simply because modeling this distributed capacitance directly to solve our problem becomes a very complex issue. Okay, we cannot, it's a mathematical nightmare. How are you going to start measuring and calculating and adding up all these capacitance to come to your final transmission line parameters calculation? It's impossible. So instead of doing that, we just lumped the transmission line capacitance at the center of the line, like you see here. These capacitance basically just become a single capacitance at the midpoint center of the line. This is a mathematical simplification to just allow us to calculate the voltage drop across the line and find the sending end current as well as the receiving end current parameters and whatever parameter that you want to work out in this transmission line model. Great. Now, having said that, I hope you now have the necessary background information where this nominal T model is coming from. Now let's start solving this problem. So reading and understanding your problem statement is very crucial to avoid you making mistake, knowing exactly the known and the unknown parameters. So we got a 3-phase 50 Hertz overhead transmission line like what we're seeing here. Now the power at the receiving end here, that's PR 100 megawatt, the line voltage 110, power factor 0.8, lagging, inductive load. Okay, now we've got a resistance per phase here, 30 ohm and 40 ohm, and these capacitance, the lumped capacitors at the midpoint here. Now we need to calculate the voltage, current, and the power factor at the sending end. So obviously, like we did before, the first step here is to establish what you have, basically your given data, active power, power factor, and determine the angle at your receiving end. We explained it in the previous tutorial. Then at the receiving end, we've got a line voltage of 110 kilovolt and the per phase parameters. Okay, now this is where it gets interesting. Now we know that the parameters at the line here, they were given per phase as 30 ohm for the resistance and 40 ohm for the reactance. Okay, these are the series impedance. Now because this is a T model, we have to divide it because each series impedance is going to fall at each half of the transmission line, okay, while the capacitance of the line is modeled at the center of the line. That is why we've got the Z per phase here to be 15 plus 20J. Okay, so that is for this section and this section as well. Same parameter. Now when you work it out, you've got 25 with an angle of 53.13 degree ohm. Moving on, the shunt reactance, obviously XC 600 with an angle of negative 90. Step 1, convert the line voltage to phase voltage. Very simple. So that is 63.5 kilovolt. Step 2, calculate the current at the receiving end. Okay, now this is your current at the receiving end flowing to the load. Okay, now to calculate this current is very simple. You just need to know what is the voltage that is driving this current, and that voltage is already given to us here as 110 kilovolts. So very simple, we can deduce
and calculate the current at the receiving end using the 100 megawatt of power and the line voltage. I already explained this formula in the previous tutorial. So we find this current here of 656.08 amp. Okay, now this current have an angle here that is negative 36.87. So our phase angle for the current give us the total statement for the receiving end current. Now we continue with the step 3, which is to calculate the voltage across VC. Okay, now if we didn't have this line impedance here at this section, we will just deduce that this voltage VC is the same as this voltage at the receiving end, obviously per phase parameter. Now, because we've got this series impedance on this section of the line, we have to take the voltage drop across this series impedance and add it to the receiving end voltage to actually get the voltage across the lumped capacitance. Okay, so we can name this voltage as VZ2, okay, which means at this section here, this is going to be VZ1. You can name it whatever you want to name it. Okay, so having said that, we can continue. By the way, please thumbs up if you find this tutorial useful. I thank you so very much. Then that means V per phase is VR plus VZ2. That means VZ2 is actually IR times the series impedance, because the current flowing here is exactly the same current flowing there. Very simple, Ohm's law there. Okay, and we can calculate VZ2, which is the current times the impedance per phase. And one thing to remember is this line current, okay, it is equal to the phase current in a star connected transmission line. I explained that in the previous tutorial. Okay, now moving on, we found our VZ2. We continue, then that means VC per phase is then the combination of this small voltage drop plus the receiving volt per phase, which is 63.5 kilovolt. Obviously, angle is 0 degree, and this one, the angle is 16.26 degree. So we find a VC per phase that is equal to 79.38 with an angle of 3.3 degree kilovolt. Now we move on to step 4. Okay, now we know what is the voltage here across this capacitance, so which means this voltage is actually going to help us find the current through the capacitance. Okay, that means this voltage is driving this current. Remember, the voltage is a pressure that drives the current. Now we're going to find our IC here. Very simple, and that is VC per phase divided by XC. Straightforward, we found the current IC 132.3 with an angle of 93.3 degrees amp. Continuing, step 5. Now, since we now find this current, again, Kirchhoff current law, so which means I sending here must then be equal to the sum of current leaving this particular node here. So that is IC plus IR as per the previous tutorial. And that means IS, okay, is equal to IR, which is this particular current per phase, okay, plus the current IC, which we basically calculated here. So we find this current IS to be the sending end current. Straightforward, very simple, guys, but you have to understand the methodology that you are doing here so that you don't make mistakes. Now we move on to step 6, voltage at the sending end. Now, since we now know what is the current across these series impedance here, it is now very easy for us to calculate VZ1. Okay, that way we can take this voltage and add it to this voltage to find the voltage at the sending end. There you have it, guys. So very simple. Then you've got your problem solved and get the full marks. Okay, so moving on, Vsend is obviously Vc with an angle, Vc theta with an angle plus Vz1 with an angle. Okay, Vz1 is Is times Z per phase at that section of the line. We know it is exactly the same here, okay? And the current IS, we just found it there. Then we find VZ1 to be equal to 14.5 with an angle of 26,33 degrees kilovolt. And from here we can go ahead and calculate our Vsend by simply adding VZ1 plus the Vc that we found here, okay? 79.38, there it is, plus the VZ1 that we found there, and we can actually calculate Vsending per phase to be 92.9 with an angle of 6.8 degree. And if you want to calculate the Vsending of the line, you just have to basically multiply this value with a square root of 3, and that's going to give you the sending end voltage of the line. Great stuff. Now moving on, step 7, the power factor at the sending end. Now this is very important because the power factor at the sending end is what's going to help you find the power at the sending end, okay? And once you have the power at the sending end, like we said in the previous tutorial, you can find the efficiency and many other parameters that are necessary for your line. And the power factor at the sending end is always the combination of the angle of the sending end current with the angle of the sending end voltage, okay? So that's cos of angle between IS and VS, okay? So if you have to compute this with your calculator, is very simple. So it's cos of 26.8 plus 6.8, which is the angle here of the sending end voltage per phase, okay? You close your bracket, equal, then you're going to find 0.83. Now this is the power factor which is lagging at the sending end of the line, okay? Now from here, like I've said earlier, you can get the power at the sending end and get the efficiencies. You already know what is the power at the receiving end, 100 megawatt. So that is it, guys, for this tutorial. I hope you found it useful, and if so, please make sure you give it a thumbs up. Subscribe to CMTEQ channel so you not going to miss more tutorial of this nature, unlocking more power system concept for you. Thank you so much for joining. Until next time, cheers.